Again, please. All right.
It's 12:30.
Okay. Yep. Hang on 1 second. Sorry. I missed that. Okay. All right. So what I need you to do real quick. You see the paper that I rolled out there? Well, so you can either roll. There's a cutter there, like a station opener that you can break down it. But I fold and then put like two together in a roll, make 6 separate. Yeah. That's what I need. So you do. Okay, thank you. All right. Divine, get a moment, take off your headphones. All right. All right. So today, ladies and gentlemen, we are going to talk about kinetic and potential energy as well as a few other things. So let me hand some stuff to you. All right. Juana's still not here. Can't give that to him. Okay. I started grading your labs that you turned in yesterday. If you didn't grade it, if you didn't turn it in, I cannot grade it, and it is now late. So please make sure you take care of getting it turned in so you can get some points instead of none for it. Okay? If you were not here for the explanation of the lab that I went through yesterday, you have two choices. There is a video online that you can go to and you can watch the video, or you have to come in and see me, or you have to figure it out on your own. So I guess you have three choices. Okay? You can come and see me during home base or advisory period. You can come and see me before or after school. Again, you could watch the video and it talks you through how to do everything on the lab that you need to do to finish it up. But if it didn't get turned in, it needs to get turned in, needs to get finished, and needs to get into me. Okay? So that's what we got for there. All right? Today, again, we're going to start talking about kinetic and potential energy. So if you would, ladies and gentlemen, open up your EISN and go to slide number 21, please. Slide number 21 is the start of where we're going to talk about two laws. Now, there are very few laws in nature. There are a lot of what we call theories, but there are only a few laws. Laws are proven over and over again to be mathematically true, to be mathematically correct. Okay? And two of those laws are the law of conservation of matter and the law of conservation of energy. Now, these two laws are almost identical. There's literally one word difference between them, okay? Matter cannot be created or destroyed, only changed. Energy cannot be created or destroyed, only changed, okay? So these are the two laws that will govern almost everything we do in chemistry, and if you decide to take physics after this, they'll concentrate a lot more on the law of conservation of energy, but we, again, cover it in this class as well. What that means is that the mass before a chemical reaction cannot change afterwards. So however much stuff you start with, you have to end with the same amount. Now, this doesn't always seem practical, and it isn't always practical. Because one of the things people always use is the example of a fire. Okay? So you throw a big log on a fire, you let it burn, and at the end you've got some ashes left. And people are like, there is no way that that is the same mass as the log that was burned beforehand. And I agree with you 100%. It is not the same mass. That does not mean we're violating the law of conservation of matter. What that means is when you burn a log, when you have a fire, it is what we consider an open system. An open system is one where things can leak into the environment. Okay? So for example, when you burn a log, you give off smoke, you give off debris, you give off things that go off into the air, and that's part of the mass that you are trying to conserve. So, doesn't always work out that way. Second semester of this class, we are going to do labs where you are going to be able to, before you begin the lab, predict exactly how much stuff you should create in the lab. And you will do that because nothing will go off into the air. Nothing will escape. We will be able to do experiments where we will be able to contain everything that goes on, and we will be able to prove the law of conservation of mass. Okay? This applies to chemical changes. Okay? In a physical change, we're not actually changing the matter at all in terms of what is there. We are talking about changing its appearance, changing how it shows up, things like that. And then there's what is called the law of conservation of energy that says energy cannot be created or destroyed. It can only be changed. Okay? What I mean by that is, right now, the box sitting up here has a type of energy. If it were to fall from the top here, it would have a different kind of energy. But the energy that it has now can't be any more or any less than it ever has unless we do something to it. And if it starts falling, well, that energy may change to a different type. We can't get any more energy than it has right now being stored up there, and we won't end up with any less. Okay? So that is what we are going to talk about today. Law of conservation of energy applies to chemical and physical changes. Okay? So this is kind of an overview of what we are going to talk about. All right. So next slide, ladies and gentlemen. All right. There are some terms that we need to define. So the first thing I'm going to do, I'm going to put them all up here for you. I'm going to give you a few minutes to copy them into your notes, and then we will talk about them rather than me talking about them and you trying to listen while we can't do that very well. Okay, are we all good? All right. Matter we have already defined for you. It was the first thing we actually defined in this class because chemistry is the study of matter. Matter is anything that has mass and takes up space. And we said originally that was almost everything around us. Very few things are not matter. Time, gravity, thoughts, ideas, emotions, those are not matter. Okay? But the air that we breathe, the table, the things that you have on your desk, those are all matter. They all have mass. They all take up space. Mass is the amount of matter that an object contains. Now, you will hear science teachers especially talk about a difference between mass and weight. And there is a difference between mass and weight. Mass is the amount of stuff that makes something up. There is a certain amount of stuff inside you that makes you up. Now, you also have a certain weight. But your weight is determined by where you are at. Meaning because we are on planet Earth, ladies and gentlemen, there is a gravitational attraction between us and the planet. And that gravitational attraction is what gives us our weight. So that is determined by the amount of mass inside your body and the pull of gravity on that matter. Okay? Any object that has matter creates gravity. Any object, okay? Even something as simple as this marker. Because it is matter, it technically has gravity. And because of that, it is attracted to other objects that have gravity. In other words, other objects that are matter. Now, the problem is this marker is attracted to the most matter-rich thing around us, which happens to be what? What is the biggest piece of matter around us? Right? No. Not even close. The Earth. The Earth. The Earth is the most massive thing around, ladies and gentlemen. And therefore, this marker is attracted to the Earth. Okay? Now, the only way we could avoid this would be to do what? To get away from the Earth. If you or I were lucky enough to ever get to travel to the moon, the greatest weight loss program in the history of the world, because as soon as you arrived on the moon and you took your weight, you would weigh 1/3 of what you do here on Earth. Sorry, 1/6. So if you weigh 180 pounds on Earth, on the moon, you weigh 30 pounds. You weigh 120 pounds on Earth, on the moon, you weigh 20 pounds. 1/6 of whatever your weight is, that is what it will be on the moon. Why? The moon is a lot less massive, has a lot less matter in it than the Earth does, and therefore has less of a gravitational attraction to it. Okay? Has less of a gravitational attraction to it. But if you were in outer space, away from everything else, and you let this pen go, it would be attracted to you. Why? Because without something else that has a larger mass than you do, this is going to be attracted to whatever the most massive object is around. Okay? So, just something to think about. That someone special who you've been wanting to, find you attractive, take them into outer space, be the most massive thing around, they will be attracted to you. Okay? Just whatever you do, make sure you don't take Mr. Nast with you. Okay? Nothing. Anna's got a smirk on her face. Now, here's the one thing I do know. By the end of the day, Mr. Nast will be calling me. Because one of you will rat me out that I told this part about him, which I do every year in class, so he's used to it. But one of you will tell him that I said he was the most massive thing around. Okay? He's not actually, but that's a whole other story. Anyway, energy, the ability to do work. Now, work has a very special definition in chemistry. Work means you apply a force and you have to move something some distance. If I push against this door, am I using energy? You're shaking your head no, Jonathan. Okay, come here, though. Come on, hurry up. Push against that door. Push hard against it. Push hard against it. Are you using energy?
No, yeah.
What do you mean? No, I wasn't. Now all of a sudden you are. You didn't move the door.
Very little.
What are you saying about my energy?
You're using very little energy.
So you were using very little energy.
Since I was pushing it harder, I was using more.
Oh. So can you use energy? Yes. Did you do work?
Yes.
No, you didn't. Because what did you say about the door? The door didn't move. So that's what we mean when we say energy is the ability to do work. You can use energy and you don't have to do work. Okay? Because technically the definition of work is we would have to move this door some distance for it to be work. We didn't do that. You push against a large boulder trying to move it. You're going to get tired. You're going to use energy. But technically you're not doing work unless you get that object to move. Okay? So that's why we say energy is the ability to do work. Gravity is the force of attraction between the center of mass of two objects. Again, any two objects that have mass will have gravity between them. It's just that you and I are stuck to the most gravity-bound thing around, which is the Earth. Okay? Which is the Earth. All right? Technically, we said if you go into outer space, you will weigh less than you do here on Earth, right? If you had a scale fine enough, even on an airplane, you would weigh a little less than you do on the surface of the Earth. Why? Further away from it. What's holding that green, blue, and kind of pinkish, I don't know, clips onto that door frame? Magnets. So there is a force that is holding these things together, correct? Now, please stay with me. If I move this over here, did I shut off the magnetism? It's still there, correct? Because if I bring it back, boom. So you can never shut off magnetism, right? But if I move it far enough away, now instead of sticking to there, it falls to the ground. Why? Okay, and how did it get affected by the distance? It went what? Well, right here, it's sticking to the frame, correct? What other force is acting on that right now? Give you a hint. What force? What? Is gravity still working on these right now? Why isn't it pulling them down to the ground? What? The magnetic force is stronger. Simple rule in science, ladies and gentlemen. Strongest force always wins. Strongest force always wins. I move the magnet away from the door frame. What becomes the stronger force? Gravity, pulling it down. Why? This distance makes it so the magnetism isn't so strong. I bring it back close. Boom, the magnetism takes over. It holds it up. Magnetism is the strongest force. Okay? Magnetism is the strongest force. So the same way for you and I, if we get further away from the Earth, we feel less pull to the Earth. Okay? We feel less pull towards it. So technically, if you're flying in a plane, you would weigh a little bit less than you do when you are on the ground. Because you are further away from the center of that mass. Further away from that force that is pulling you there. By the way, a force is simply a push or a pull. That is the easiest way to describe a force. You push something or you pull something. Okay? Questions? Awesome. Now, here we go. All right. There are two basic kinds of energy. There are lots of forms of energy, but there are two basic kinds. Potential and kinetic. Potential means what? Has anybody ever said you got a lot of potential? What? Okay, it's being stored, or it is being held there, right? Okay? Potential energy is energy that is stored in matter because of one of three things. Because of its position, because you deform it, or because of the bonds that it has. So are these boxes deformed? Do you know what deformed means? Not in their regular shape. Are these boxes deformed? Okay, do these boxes have position? Okay, to have position you need to be above what? Give you a hint, you stand on it all the time. The ground. These objects have potential energy because they are above the ground. What kind of energy is this? What? It was once I let it go. Up until then it was potential. Because what did I do to the rubber band? We deformed it. We took it and we changed its shape. It then went back to its shape and released that energy. That is what we mean by deformation. And finally, ladies and gentlemen, bonds, think about the fact that you can light a match. Where does the energy for the match come from? It comes from the chemical bonds inside that match. Energy stored in there that is released when it is burned. Okay? So, you can have position of matter, deformation, or bonds. Now, the most common one of those that we are going to deal with is energy of position, meaning it is stored up high. But if you think about it, if you have a bow and you pull a bow back to fire an arrow, which one of the three is it? Position, deformation, or bonds? Deformation. The food that we eat has potential energy in it. Is that because of its position, its deformation, or the bonds in it? The bonds. The bonds. When we eat food, we break down the bonds, we get the energy from it. Okay? A bird sitting on a wire has potential energy because of which? Position, deformation, or bonds? Position. It is high above the ground, it can fall. Okay? High above the ground, it can fall. Now, potential energy depends on two things that we control and one that we cannot. It depends on the mass of the object and it depends on the height of the object. Those are the two variables that we can control. We can control how heavy something is, or we can have things that have different masses. We can also have things that have different heights. Okay? There is a third thing involved in the formula, though, and that is one thing that we cannot control, and that is the thing that would cause that object, if it came off the shelf, to fall to the ground. And what is that? Gravity. Gravity. We cannot control gravity. It is technically a variable, ladies and gentlemen. It is just one that we will never change here on Earth. Okay? So technically, I guess we could put a third variable in here. We could put gravity in here as well. It's just that we really cannot change it. Okay? So to be a variable, it should be something that changes. Okay? Now, the units for all of this stuff here are something called joules. Okay? The unit for energy is called a joule. Now, I am not going to make you do calculations calculating the potential energy in something. Taking the mass of the object times its height times gravity. You want that? Go to physics. They'll give you that all the time. Okay? We are not going to do that. Okay? I do expect you to know what the variables are. We will talk about how these variables affect this in just a minute. Okay? Now, kinetic energy, ladies and gentlemen, kinetic energy means that an object needs to be what? Moving. Kinetic energy is energy that is caused because of motion. Any type of motion causes kinetic energy. Now, the boxes on that shelf, are they moving? So they have no what? No kinetic energy. An object must be moving to have kinetic energy. Okay, has to be. If it's not moving, it has no kinetic energy. There are two variables that affect kinetic energy. They are the mass of the object, again, how heavy it is, and the velocity. Anybody know the difference between speed and velocity? They're almost the same. One slight difference. Velocity is with direction. Thank you. Velocity is with direction. So, how fast is it moving and in what direction? And we could use things like to the right, to the left, up, down, north, south, east, west. Anything that gives it direction as well. Okay? Anything that gives it direction as well. Now, the formula for kinetic energy is 1/2 mv squared. Okay? Again, not going to make you memorize this formula, not going to make you do calculations with it, but this is the formula for kinetic energy. What's the unit? The unit is joules, because it doesn't matter what kind of energy it is. Energy is energy. Whether it is kinetic, whether it is potential, energy is energy, ladies and gentlemen. Does not matter what kind of energy it is. Questions? Anyone need more time? Okay. So then we're going to do a little activity here today, ladies and gentlemen. We are going to look at the two variables that affect kinetic energy. Okay? We're going to look at the two variables that affect kinetic energy. And we are going to use these three objects. This one, and this one to help us. Now, I know they're not exactly the same shape, but what is the biggest difference between this object, and this object that can affect kinetic energy? Their mass. Their mass. Obviously the most massive, correct? Middle mass, lightest mass, correct? Okay, good. So here is what is going to happen, ladies and gentlemen. In a minute, you are going to go in back of the room. And you are going to take the book and you are going to slide it across the table to a partner. Okay? So you are going to stand on one side of the table. Your partner is going to stand on the other. And you're going to take the book and you're going to push it to them. Each of the three books. Okay? And you are going to rank them. You're going to push it to your partner is going to push it back to you. But when you push it, you want to try to push it so that it is the same speed each time. So no matter what the book, you want to try to push it so that it is the same speed each time. So we are looking right here at leaving the speed constant and the mass variable. Different size books, different masses. But when you do this, you've got to push it so that it goes across the table at approximately the same speed. And then you and your partner are going to make a judgment. And the judgment is going to be a simple ranking system. Okay? A simple ranking system. 1, 2, and 3. For which one was the easiest which one was the middle, and which one was the hardest to either push or stop at the same speed. So you are going to put in here 1, 2, and 3. Okay? 1 being the easiest one to get it across the table to your partner at a speed. 3 being the hardest one to get across the table to your partner at the same speed. So you are going to test the kinetic energy by leaving the speed constant and changing the mass. Questions? Okay. For number 2, we are going to leave the mass constant, meaning you are going to pick one of these 3 books. One of them. Okay? And you are going to make the speed the variable, meaning I don't care which one you choose, but I'm going to push it to my partner, and I'm going to push it slow, then I'm going to push it faster, then I'm going to push it faster still. And again, you are going to rank which one was the easiest and the hardest to stop. Was the one with the most velocity harder to stop than the one with less velocity, or was it the other way around? And the nice part about this is whether you are pushing or whether you are catching it. You can either judge it by how hard it is to push it that way or how hard it is to stop it that way. Questions? Then over here, ladies and gentlemen, you are going to tell me what you found out about the kinetic energy as we change the mass. So what do you think this ranking means for the kinetic energy when we change the mass? So as the mass increased, what did kinetic energy do? Did it increase or did it decrease? And then how do you know this? And I'll give you a hint. How you know it is because of how hard it was to stop. Was it easy to stop or was it hard to stop? Okay? Then you're going to do the same thing down here for velocity. Increase the velocity, the kinetic energy. Did it go up or did it go down? And how you know that. When you are done with that, you have one more to do, ladies and gentlemen, and that is our next slide, and that is slide 25. Now, we're now going to take a look at potential energy. So again, potential energy, 2 variables, the mass and the height. So we are going to leave the height constant, and we are going to adjust the mass. I need a volunteer, please. Can someone come up to the front for me? Don't be shy. I'm not going to kill anybody today. I'll save that for later. Thank you, Jade. Okay. So, Jade, you're going to put your hands out like this. Okay. I'm going to take and I'm going to drop the heavy object for you. And I'm going to do it from about the same height. So I'm lining this up about with the top of Jade's head. Jade catches it. Now he needs to decide, was that easier or harder to stop than that one? And you can switch off. You can do it once. Your partner can do it once. That's changing the mass, same height. So I'm holding it at the same height, about the height of his head, releasing it. He's putting his hands at the same place. Okay? Now, pick a book, Jade. This one? Yeah. Okay. You're going to pick a book the second time. And in that yellow line at the top, and I should have told you this on the last one, please tell me which one you are using. The light mass, the medium mass, or the heavy mass. It's your choice. Okay? So now Jade puts out his hands. We're going to drop it from a low height. We're going to drop it from a higher height. Okay? And then we're going to drop it from a high height. Okay? There's a step stool on the back of the middle table if you want to stand on the table in the back when you do this. Please don't kill your partner. Don't drop it on their heads. Hit their hands. And please, do what Jade did. Catch the book. Don't drop it. Okay? Thank you, sir. So, when you are done, ladies and gentlemen, again, your ranking, 3, 2, 1. Be consistent. I don't care if you say 3 is the easiest or 3 is the hardest, but be consistent. And then you come over here and you fill out the summary part. Questions? Partner up, 10 groups of 2. There are 2 of you. There are only 3 books at a station. So when one group is using one, the other group has to use the other because I don't have enough for everybody to go around. Let's go, let's go, let's go. Come on, let's go. Nap time is in the morning. Come on. Here we go. There's that. Make sure you don't wipe out your computers while you're doing this as well, please. Put them in a place where they will not get wiped out by the books as they're sliding across the table. You gotta at least make them across the table. Come on. Who's your partner? Okay. Go ahead. Hurry up. Tell me she knows. You can make up your own mind on that just so long as you're consistent. Right? Okay. You gotta at least make it to the person. It shouldn't stop before it gets to them.
Like that? Wait, are you ready? No, you're ready. 1, 2, 3. I think you do
So, did we already do heavy notes?
Yeah.
Okay.
Did you do the heavy notes first? It was like oh, well, that was easy. It is sick.
I give them.
Number one, it was like getting so like.
Let me write it down. Medium, I give it
You didn't have either one. Life would be so much easier.
Oh, that was a lot easier.
No way.
You think you would be a lot happier?
Okay.
So in other words, you never want to be able to stop.
No, that was hard. That was hard.
No, I feel like this is harder.
Actually, yeah.
Oh.
Oh, okay.
It would be interesting to see how the system would happen.
I think this one's slightly easier though. But that one just slides easier.
Divine, where are you going? You need to let me know, okay? The nurse is not that way, Divine. This way? Take another left at the next corner.
Oh, we've got one book per one's like low velocity, big ones, medium ones would be like this one.
Okay, but are they all the same amount of these? So that's what you're asking yourself. I didn't say this had to be difficult. Don't get mad at each other and turn this into a war.
Chemistry.
That is a book of constants for chemistry. That is Google before it was Google.
I love Google.
That one of us does.
You know what Google?
No.
Because philosophy story?
What? I had Safari.
That's good.
Google is a better search engine. I don't like Google as far as documents and spreadsheets.
No, that.
They only really need one.
What? Well,
I think we'll be able to vision.
That's what the.
apparently not up there.
Sure.
Well, I don't see it. There's one in the back.
Preferably not standing up.
Okay, so that's number one.
Thank you.
They can take a very easy assumption. No.
Okay, wait, so how are we?
Emotional energy.
Here you go, Kalani. You're welcome.
Oh, yeah, I don't know. Oh my god, I used an excuse to go on the news.
I'm not surprised how.
I don't know.
Why is it so?
It'll kind of.
So is it gonna go with water? This is just my They both kind of like very heavy. We don't have it.
Never made it.
Sure, what happened?
We were sliding it, and then my hand hit the corner of one of the bugs.
We're gonna be okay?
Yeah.
Oh, that was easy. Okay. Girl, you were serious. Go home. I feel like this one's. Oh, yeah. Oh, light work. I think that's hardest. That is medium. Like one. I would put light. So we're putting light back, so it's covered. Has a lot of weight. Yeah. No, it couldn't be light. I think it would be. That was just the stuff. I said the heaviest match. Medium velocity. No, medium because it's easier to push. Why isn't it working? And with the next one, it's like that was pretty heavy. Yeah. Wait, what? Wait. Am I on the wrong one? Alright, what's the number? Wait. Wait, I think I did. I'm still sliding or something. No, I'm gonna do how to catch the object. No, that's what we're doing. For what? There's two more buckets with two more. Yeah. And then two. Medium heavy. Yeah. Okay. Okay, now we're doing okay, mine. Do you want to catch up this time? Sure. Heavy, medium, or low?
Yeah, that's what it's for.
For the high.
Bleeding or not?
We have an extra charger.
What was the hardest one?
I can go in back and see if there is one. Sure.
That was like rad. Like the whole thing.
We were sliding this boat, and then it hit the corner, like the corner hit my knee. I don't know when you really touched it.
Aiden, here. Let's just do this.
You just take this and hold it. So, are you gonna get the knee surgery?
What?
That's the second time.
Yes.
So what do you plan to do? Because I don't know if my key doesn't work. It's so lame.
What if it just starts with suck?
I like this.
Thank you so much.
Why did my whole body bounce? The throat.
Clearly.
Okay, we want to be done in the next few minutes, please. So get finished.
Wait, no, we can't do this. We can't do this. One more. It's just one more.
Good.
That one hurt.
I have one.
You're doing it. Why am I looking at
This may be the first class.
My parents won't hear my
All right. So we're going to use this slide to summarize what we just learned, ladies and gentlemen. Now, here's what you're going to do with this slide. I'm a visual person. I like visuals. In the first part of the experiment, we held the mass constant, and we changed how fast the book was slid across the desk. So when we did that, ladies and gentlemen, if the book was moving faster, that means its velocity increased. So tell me what you think happened to kinetic energy by clicking on the either up arrow or down arrow and dragging one to right here and the other one to right here. So when we increase the velocity, what happened to the kinetic energy? Did it go up or did it go down? Okay, so that is what we are asking you. So you tell me, when we slid the book faster across the desk, was it easier to stop or harder to stop? Don't everybody shout it out all at once. It's okay. Harder, which means it had more or less kinetic energy. More. So when we increase the velocity, the kinetic energy increases. What happens when we decrease the velocity? The kinetic energy decreases. Okay. Now, what kind of relationship is this from the first unit? They're both going in the same direction. Actually, it was earlier in this unit when we were talking about graphing at the start. Both are going up, both are going down. What kind of relationship? So please take and click on the box that says inverse and get rid of it. We don't need it. There you go. There's your whole summary. So in other words, ladies and gentlemen, if an object is moving faster, it's going to have more energy than an object moving slower. Very good. Now, I realize this is probably common sense, but sometimes until you do it, you don't actually realize it. You did it. Slide 27. Now we're going to hold the velocity constant. Now we're going to slide the 3 different books across. So the heavier book, was it easier to stop or harder to stop than the lighter book? Was it harder to push or easier to push than the lighter book? Harder. That means kinetic energy is increasing. Okay? So that means that if the mass goes down, kinetic energy goes down. What kind of relationship? Direct again. They're still both going in the same direction, ladies and gentlemen. They are still both going in the same direction. Okay? So again, both going up, both going down, that is a direct relationship. Okay? Now let's take a look at potential energy. We held height and gravity constant. We increased the mass of the book, we decreased the mass of the book. Which one was the hardest one to stop? Lightest, medium, or heaviest? Medium? The medium one was harder to stop than the lightest? The medium was easier to stop than the heaviest? Well, let's think about this for a minute. If the medium one were the hardest to stop, would there be any pattern here? Okay, let me ask you this. Let's take it to an extreme. Someone drops a penny on your head from 2 feet above you. Is it going to hurt? Someone drops a 16-pound bowling ball on your head from the same height. Is that going to hurt? Okay, so what is increasing the mass due to the potential energy? Increases it. Increases it. So therefore, if the mass decreases, potential energy will decrease. What kind of relationship? Still a direct. We may want to see an inverse relationship, but we're not. That's the fact. These are all direct relationships so far. Okay? So now, if you held the book higher, whichever one you did, was it easier or harder to stop the higher it got? Harder, meaning more potential energy. Lower height means less potential energy. What kind of a relationship? Still a direct. That doesn't change. Still a direct. Questions? Okay. So now let's take a look at some questions. Okay. So I'm going to grab this handbook again, the CRC handbook. Right here. Describe its kinetic and potential energy right now. Both. Tell me what its kinetic is, tell me what its potential is, and why. Ayla, which one do you want to describe? Kinetic or potential? Kinetic. What kind of kinetic energy does it have right now? What? None. Absolutely. Why? Why does it have no kinetic energy right now? That's Stephanie. Good. It's not moving. For an object to have Kinetic energy, it must be moving. Good. All right. Safira, how about its potential energy? Why? It's what? Where is it storing the energy? Okay, but now you're talking about kinetic. When you talk about moving, we are strictly talking about kinetic. There are two different kinds. And is that object moving? No. So it has no kinetic energy. Potential is energy of position. So to have position, you have to have height. What's the height of that book above the ground? Is it above the ground? So then what kind of potential energy, how much potential energy does it have? None. Why? Because it is sitting on the ground. Okay? So, what kind of energy, kinetic energy does it have? None. It's not moving. What kind of potential energy does it have? None. It's not above the ground. And yet every year when I do this, there'll be one kid in class who will be like, well, Mr. Brand, I can prove that that book has kinetic energy. Okay, how? How could somebody claim that that book has kinetic energy? You guys might be my first class ever that didn't try to come up with a way. How does that book right now, and they're right every time they say this, how does that book have kinetic energy? I agree with you. The book is not moving. Not trying to claim that it is. Sometimes you need to look a little deeper. Jade, you seem to have a thought come through your mind. No? You're just getting excited about something else later on today? Anybody? Anybody know how you could claim it has potential energy? Because it definitely is not above the ground. No, the floor is not going to open up and it fall down to the first floor either. How could that book have potential energy still? Come on, you got to get 1 out of 2. Look back at your definition for potential. Where's there still potential energy in that book? What? Ethan, I'll tell you what, if you answer this incorrectly and you die from it, I will never ask you another question in class again. Hey, quiet. I don't need your help here.
Bonds.
In the bonds. What can I do to that book to release the energy in those bonds? We could burn it. We could burn it. That book, even on the ground, still has potential energy because you could burn the pages of it. That is potential energy. It's a different kind of potential energy, but that is potential energy. All right, one last chance. Anybody figure out how it still has kinetic energy? Everything around us, all matter, is made up of tiny, tiny particles. What? Or molecules. Yes, absolutely. Those molecules are always what? Isn't that kinetic energy? So how does this book have kinetic energy? Its molecules are always moving. Its molecules are always moving. The molecules in that book, even though we can't see them, they are always moving, ladies and gentlemen. That is how every object always has some kinetic energy. Now again, it all depends on how you want to look at it. You want to look at the book overall, the whole book. Sitting on the ground, no potential, no kinetic. It's not moving, it's at its lowest point. But if you want to look at the particles in there, and we want to talk about the energy between the bonds that we can release when we burn it, or you want to talk about the fact that the particles are moving, that is kinetic energy, ladies and gentlemen. That is kinetic energy. All right. An elephant and a mouse run a race, and they tie. Tell me how their kinetic energies compare to each other. Now, before you do that, I want you to think of three things. Number one, kinetic energy is energy of what? Motion. And number two, we just learned that two factors affect kinetic energy. What are they? The what and the what? Okay. Now, if any two objects run a race and they finish tied, tell me what that means in terms of mass and velocity. What does it mean if they end up tied? What does that tell you? Okay, apparently no one in here has ever run a race. And you can't tell me what it means if two objects end up tied at the end of a race. Jonathan and I run a race. 40-yard dash outside. We end up tied. We cross the line at the exact same time. What is the same for us? What? Our speed. Our speed. Now, you are going to be nice when you answer this question. Jonathan gets to represent the mouse. I get to represent the elephant. Because what is different about Jonathan and I? What is different about a mouse and an elephant? Their masses. And again, be nice when you answer this. How do our masses compare to each other? I like the way you went back to the elephant. The elephant has more mass. Well, of Jonathan and I, who has more mass? Now, we are moving at the same speed, correct? Think about what we just learned in the lab. What does that mean for our kinetic energies? Two objects, same speed. Different masses. What does that mean for our kinetic energies? Light book, heavy book. Sliding them across at the same speed. Which one has more kinetic energy? The heavier book. The heavier book. If we're running a race and you accidentally walk out in front of us at the end and we're about to run into you, who would you rather be hit by? Why? He has less mass. He's going to have less kinetic energy. Okay? I have a larger mass. I'm going to have more kinetic energy. A baby and an NFL lineman run a race. They finish the race with the same kinetic energy. Who wins? I have really bad news for you, ladies and gentlemen. really bad. You are going to struggle for the rest of the year if you're going to be this quiet and you're going to wait for somebody else to give you the answer to all these questions. Because while you may think you're learning it, you're probably not. And your next test is a lot on these concepts and ideas that we are talking about right now. So you tell me, mass, velocity, kinetic energy. These two objects run a race. They finish with the same kinetic energy. What is different about a baby and an NFL lineman? Their mass. Which one has more mass? Okay. So what is the only way a smaller, less massive object can have the same kinetic energy as a more massive object? It has to have more velocity. So who wins the race? The baby does. The baby has to win the race. Why? The only way it can have the same amount of kinetic energy as a heavier object is to move faster. Meaning, ladies and gentlemen, when you think of kinetic energy, you need to think of those two things. You need to think about the mass and you need to think about the velocity. Are the masses the same or are they different? Are the velocities the same or are they different? Is the kinetic energy the same or is it different? When you start thinking about that in terms of those things, you're going to be able to understand a lot more of what we're going to talk about over the next few days. Two roller coasters are stopped at the top of its tallest hill. At the same time, the dual coasters that are racing, and it is stopped right at the top of its tallest hill. How is it possible they do not have the same potential energy? What? I want you to be a little bit more specific because I don't think anywhere in our formula there was amount of people. But I think I get where you're going with this. Thank you. Less mass in one cart than the other. Again, we can't really say less amount of people because it depends on the people who are in each cart, correct? But if one cart does not have the same mass as the other, even at the same height, they will not have the same amount of kinetic energy. Right? The one that has less mass is going to, sorry, I said kinetic energy, I meant potential, my bad. Okay? How is it possible for a bowling ball and a golf ball to have the same potential energy? What's different about them?
One might be higher than the other.
Okay, which one has to be higher? Why?
It's has less mass.
You bet. Again, the only way that something can have the same kinetic energy as a heavier object is to be moving faster. The only way it can have the same potential energy as a heavier object is it needs to be higher up. Very good. Very good, ladies and gentlemen. We got through. Nicely done. Nicely done. Tomorrow's another day, ladies and gentlemen. Another day of chemistry. Excellent.